So today I'll be talking about some troubleshooting techniques or common, well, not all the common issues that we see, but a few of them. These issues are things kind of around support questions that come in on a fairly regular basis. So I thought I would do a presentation in which we address these. And it might not be exactly the issue that perhaps that you had or question you had, but maybe it's similar, and hopefully it provides some use for you if you've had similar questions. So what I'd like to do is first just talk about the a question that often comes to us in which people are simulating a rate of change of some sort, and we could say it's a volumetric flow rate or it's a mass flow rate, something like that, and then they are on a period basis calculating cumulative amounts and finding that when compared to the similar calculation in Excel, they're getting a different answer. Okay, so this is a common thing. It might come in a slightly different flavor of a question, but this is the basics here. So what I'm showing on the left is a model where you have some typical model, you're calculating flows, and then outside of that, you're doing some sort of reporting on a cumulative amount. And then in Excel, if you look over to the right, you'll see that there is a flow rate, and I color coded, by the way, cells that are essentially reports from GoldSim in orange. So these orange colored columns represent outputs in GoldSim. I just copied and pasted them from the time history, and then the green is what's calculated in Excel. Okay, so oftentimes people will have an Excel model that calculates things like quantities over time, and that's what we're doing with this integrator element. And it's really just a calculation that says what's the previous value plus the next row down, and you get some cumulative amount. Okay, so the common thing that comes into us is, well, I'm doing this, and then all of a sudden I get to a spot where they're not the same. Why? Why are they not the same? And that's what we have right here. Let me just freeze. Where was it? Right here. Here we go. Okay. All right. So it's common that we see this question, right? So we're seeing on day January 18 that GoldSim calculated a cumulative mass that Excel got a different number for. And all that Excel is doing, like I said, is it just says what's the previous amount plus the current row. And so that's all we're doing, just a cumulative accounting here. But then why is it then that GoldSim is getting a number slightly less here? And not only here, but in other various places throughout the model. Well, it turns out that in this model that we have, in this GoldSim model, I am inserting unscheduled time steps, and that's often the root cause of this particular type of problem. So if you're seeing something like this, the very first step you want to take is, find out, are we inserting unscheduled time steps? And if you're not sure, it's very easy to find out. So what you do to find out if we're inserting time steps in this model, and I'm talking about unscheduled time steps, right? Time steps that are occurring between the days here. By default, GoldSim's time history results do not report those values. They do not report those times, not by default. So you're not going to see those inserted steps here. And that's really the root of the issue, is that when we have an unscheduled step, the flow rate is not a constant. It doesn't hold at this constant value on the next inserted step. And so you will get a different answer if you're just doing a 1 day averaging calculation like this, like you do in Excel, for example. Okay, so to figure that out, go to the simulation settings, and then in here, you'll note basic step is 1 day. Okay, that makes sense. If I go to the show scheduled updates table, it shows me that sure enough, I am inserting a time history. That's H. H shows up here in the legend. H equals time history result. I'm showing a time history result on every day at midnight throughout the whole. That's the those are the scheduled updates. Okay, so if I then go to advanced, this is where we can show something different. If you check the box here that says include unscheduled updates in scalar histories, scalar time histories, that's what we want, right? Now that that's checked, this time history result is now going to show us high resolution results. Notice the labels in this display column have now changed. It now says high resolution. It didn't before. Okay, that's what it's going to show us. So when we run this model now, and we look at the table view of results, you'll see there are the inserted steps. They occurred right there. And you'll also see that when that unscheduled event occurred, the flow rate was now different than it was at midnight that same day. So that will have an impact for sure on cumulative quantities calculated using an integrator element. That is why we have a number that's different when you're looking at just the times at the basic steps. So what can you do to fix this? Well, if you truly do want your numbers to be calculated as done in Excel, then you have to avoid these unscheduled time steps. How do we do that? Well, there are a couple of ways you can do it. If you truly do not desire any unscheduled events to occur, and many people do not desire this and don't want it, then you can disable them completely. The only thing you need to that you need to remember before you do something like this is that you might want unscheduled events for some reason, and just make sure that you have to make sure you don't want them. A case in which you would want them is if you have, for example, a stochastic element that's triggering randomly, that might be, or not even a stochastic, but a discrete change, or some amount that's added to something, or some trigger that's flipped at a random time, like for example, simulating a power outage. Things like this, you would typically set up to trigger randomly. And so those kinds of events will be disabled. They won't even trigger at all if you don't allow unscheduled events. So you have to be careful with this decision. But oftentimes in water balance models, there are not events like that typically. And usually the reason for unscheduled events in those kinds of models is that you have reservoirs or pool elements in which the bounds are being hit, the upper and lower bounds are being hit. When those get hit, in other words, when the amount or quantity in the pool or reservoir element, when that value becomes equal to the upper or lower bound, at those points in time, an unscheduled event has occurred, has been added to the model. Those are most often the reasons you have them. So the other point that it's very, very important is to realize that your mass balance is still fine. The reservoirs and pools will still calculate the correct quantities being overflowed and outflowed from the reservoir if you don't allow unscheduled events. It's still okay, but the change is that those outflows and overflows are calculated as averages over the basic step. In other words, over 24-hour periods, which is precisely what it's what you would see in Excel, right? In a similar Excel model. That's exactly what you'd be doing. Is you'd be saying that, okay, it's true that the overflow might only be occurring for half the day, but we're just going to assume it's an average over the period of the day, and it just spread it out over 24 hours, the same quantity. So yeah, it's if you're trying to build a model that operates in a similar fashion as Excel, as the equations do in Excel, then you should probably disable the inserting of time steps. So just to review how you do that, you go to Simulation Settings, you go to Advanced, and then not this box. I'm just going to uncheck it because we don't need it, but you would uncheck this one up here that says Allow Unscheduled Updates. If you uncheck that, then your outflows and your overflows are now averages over the basic step, and you are not inserting any time steps. And when you run the model, you will get exactly the same answer that you get in Excel. Okay, I'm just going to reallow them now. And now I want to turn to another model that, let's save this one. I'll open another model that will show you how, I'll demonstrate to you how you can get around the situation of hitting the upper or lower bound in a reservoir. Okay, so let's go there. And for me personally, I would say at least half the time in building models, like water balance models, for example, that it is actually useful to avoid hitting bounds on the reservoir at the pool, to put logic into the model to avoid using those. And I'll tell you why when I open the model. It's not something I would say do all the time, but oftentimes it's useful because you might need more control on how you define an overflow rate, for example, than what GoldSim does by just saying it's a instantaneous amount during a specific period of time that's not within the basic step. Okay, so let me open that model now. Okay, and then I'll close the Excel file. And there's one more model. I want to open this model side by side. It's the same model, but I'll open them side by side. It's just I made a small change to one of them. Okay, and somebody has a question. Okay, somebody said, in a previous webinar, you recommended not using a previous value element if you want the value from the previous time step, even if unscheduled events are disabled. Yeah, I still agree with this. How can you, for instance, calculate the derivative of an integral without using a previous value? For instance, if you are outputting a discrete outflow from a stock element, you want to use a subset of an integrator. How can you perform a derivative on it? Yeah, okay. Well, that's definitely a good question. And there are ways without a previous value. But if your goal really is to just calculate the derivative, then the previous value element is indeed exactly the element you want. I'm sorry, in this particular case, you are right. You would want to use a previous value element, but also be very aware that it is collecting the value from the previous update, and that might not necessarily be at midnight on a basic step time, right? So it's just super important that everybody knows that if you're inserting time steps, unscheduled events, that the previous value is the value from that previous update whenever that occurred. That's sometimes the surprise that people have when using a previous value element. All I'm saying is that if you're talking about a flow network, you're simulating water flowing around in a system. And if you want to truly delay the time step to be the value from the last day, from yesterday, a day ago, essentially one day previous, then a material delay is better, in my opinion, because it ensures the mass balance It keeps track of how much material or quantity is in transit that is being delayed. So it keeps track of that volume. It works like a conveyor belt, and I feel it is best for representing flows of either liquid or solid. Um, but if you're talking about just getting a derivative of some output of information, well, then yeah, previous value is good, and it's fine. It's just, please just remember that it's the previous value from the previous update, not always necessarily on the previous basic step of it, in this case, 1 day. So it may vary. Um, and we see people calculating flow rates using a previous value and then getting a surprise when they didn't realize that the, the, the value changed in between basic steps. And so there was, for example, a spike in flow that they did not see coming. They didn't see it because they didn't realize that there are inserted steps, and then inside of that, between those basic steps, there's a very small amount of time to the next step, and therefore they well, anyway, that doesn't really matter too much. But anyway, the point is that you might get a different result than you expect. That's all I'm saying. So just be careful when you're using it. But you can get a rate of change also from an integrator, whether or not you have inserted events or not. So for example, if I put it in it just real quick, as this is kind of a side note, but on the integrator element itself, you can click on more, and then you can say, you know, let's look at an averaging period. And then in here, you can go to the outputs, and you can get the average as a rate, average rate over that constant period. Whoops, I didn't put a value in here. But if you said 1 day, then it would give you the rate of change as over that constant period of time. And that may actually be what you might be interested in, you know, in a flow, in a water balance type model. This might actually be the output that you're interested in, and that just becomes a secondary output on the integrator as a rate of change, so you don't have to use the previous value in that case. All right, so enough about that. Let me go to the next question, but thank you for the question. This is a very good question. Let me see if there's another one. It looks like actually that's all. I thought there was another question, but maybe it was deleted. Okay, well, ask again if you are still wondering. All right. So now let me talk about the difference here. Okay, so this is a model that we have in our library, and essentially it's just a simple water balance example. And imagine there's some corridor, a stream corridor or something over here on the left. Water is flowing from top to bottom. We have a diversion point in that stream in which we pull water out to feed this pond, which ultimately is used to supply water to another pond that then feeds 2 demands, noted as A and B. So these are the 2 demands that it's going to feed. And so what pond 1 does is it's like a regulating reservoir. Water comes into here and it's just held until it needs to be released, and it will send water down to pond 2 if pond 2 becomes empty. So pond 2 is talking to pond 1. And then if pond 1 gets full, it overflows over to here. And then as pond 1 becomes empty, then pond 3 sends water that way. Anyway, it's, as you can see, there's some complexity here, but it's fairly simple. There's just 3 ponds. We're supplying water to these A and B. There's some return flow that comes back. So there's a recycle of flow here. And then there's a waste stream that ends up down here. So anyway, that's the basics of it. I just wanted to make sure you kind of could follow that. And then the important point about this model is that we have an overflow. And that's what I wanted to point out here, is that there's a couple of ways to calculate this overflow or represent it. So in the model that you'll find in our library, it's set up like this. If you go to the pool element inside, this represents pond 1. It actually represents the volume of water in pond 1. And what you'll see is there's an upper bound called pond capacity. So this thing will control, holding the value to be a maximum at this upper bound and never go above it, and calculate an overflow rate that will hold at this upper bound if it's reached, if the net inflow is greater. And so, all right, so what this means is that GoldSim will insert a time step whenever this upper bound is hit. And it does get hit, and we do insert time steps when that happens. Okay, but what if, that's fine to represent overflows that way, but what if you have a rating curve? That's often the case for ponds. You might have a rating, an overflow rating curve that says something like this. Hold on. There we go. Okay, it was behind another window. What you have here is that around this level of 3.9 or almost 4, that any volume amount above that corresponds to a flow rate that's increasing at a nonlinear rate. Okay, so this is our rating curve. So we're saying at these different volumes, we'll have these values of overflow. And so then what we can do is we can just, using the current value of the volume, we just put that into the lookup table and it will tell us what the outflow will be, just a simple lookup, right? So that can be used, and then we can go into the pond and remove the upper bound completely, or just move it up somewhere higher. And this is what I often like to do, because in reality, that's what we have. Usually you have a dam, and the top of the dam would be this upper bound. You would never actually want to hit it unless you're simulating a dam breach, in which case you would, but that's pretty rare. Usually you don't want to simulate that. And so you would probably put the upper bound at the top of the dam where you would never hit it. And then you would put a spillway or some sort of outflow structure, something. You'd want to represent that as the true overflow. And that's what I'm doing with this rating curve. So the one on the left is kind of the simple way to define it. All you have to do is just tell it what's the upper bound, and it will just always hit that and never go above it. And so it's simplistic, but it's an accounting. It's an accounting tool that works well, especially if you disable the inserted time steps, because then it's just calculating the average over the time step. And I'm just talking in general here for oftentimes for water balance models, that it could be that you need more control on how you're calculating these overflows. But if you're not, you're just doing an accounting, a basic accounting of inflows and outflows, and a one-day time step is plenty, then the method on the left makes a lot of sense, actually. There's no reason to simulate the hydraulics, for example, of an overflow of a spillway or something if it's just too much detail, right? So why include it? But that's what you could do with a rating curve, but it would avoid the whole upper bound situation. And you could still run your model allowing unscheduled events, but your reservoir wouldn't be causing any unscheduled events. So that's the point I wanted to make there. All right. The next thing I wanted to talk about is the potential for adding expressions in your model that become, when you need to make a change, it causes a bunch of repetitive work, and we should try to avoid that. And so sometimes you'll get in a situation where it's like, oh, we need to make a kind of a global change, and now it's going to cause someone to have to go in and make changes in 100 different places. So we want to try to avoid those. And the reason I added this in a troubleshooting webinar is because sometimes it causes a little bit of trouble. When you're confronted with a situation where, oh, now I have to make a changes in 100 places. So how do we fix that kind of a problem? Let me show an example model. This is a model I built a long time ago, but I just wanted to point out. Let me open the browser here. Okay, so in this example, I'm going to show you the run properties of GoldSim. So I'm right-clicking in the browser and selecting Show Element Subitems, and then I'm just expanding this folder that's called Local Properties right here, because what I want to do is I want to go into the model and I want to see, like, okay, what properties are being used a lot. And if I, for example, if I go to calendar time, and then if I show day of year, if I right click and go to effects, then you'll see all these places that are affected by this run property called day of year, including the one I was just looking at right here. Okay, so if we open this, this is a selector element. If I open this up, I'll see that we have all these equations in here. And this is a really good example of a place where it could be pretty easy it could be pretty common that one of these numbers would change. These are numbers that represent times of the calendar year. Well, not leap year, but the other calendar years that are supposed to represent specific points in the calendar time to make a change. But it might be April 2nd or something. Someone might say, well, it's supposed to be April 1st, and it's supposed to always be April 1st, even on a leap year. Well, we'd have to change some logic in here, for this to work, to be exactly the way they wanted it. And you can imagine how you saw how many places that I was referring to day of year. If I go back to that, day of year. Okay, so you see how many places. This is a lot of changes to make. And it would have been nice if we could have this equation be a little bit different. So you might define your change periods, or your times of the year in which you're making these changes. You might have given them names and made an array and said, here's the month and the day of the time in the calendar year that we want to make the change. And I would do it that way. I would say, here's the month and here's the day. The reason for that is because it would properly account for leap year. It would do it the correct day and month all the time, even in a leap year. And I would define those in a table, and then I would come over here and I would say, in this if statement, I would say if we're in period A, or however it's defined, and then period B, and then do the equation. And the other thing that you'll see is there's constants put in over here, and constants should be avoided because oftentimes, you want to change those, and it's hard to find them. And so you should have these constant values in a data element somewhere. And then, especially if you want to do something like scale them up, then it would be a lot easier to deal with that. So anyway, it's important to kind of think about whenever you're dealing with, whenever you see constants like this in the expressions embedded in expression elements and in other types of elements like this, it should raise a little flag and say, we should try to expose inputs like that to make them easy to change globally, so that we change it in one place and it doesn't cause a bunch of repetitive work. Okay, the next concept I want to talk about is recursive loops, and this kind of goes back to this question earlier that was just asked, actually, and that is how do we deal, or how do we use a previous value element? And sometimes the previous value element is used to break a recursive loop. So let's go back to that pond flow model I was just showing you. Okay, so in this model, if I go up a level, then what we see here is that we have right here between pond 1 and 3, we have a circle of flow, a cycle. These depending on how the flows are calculated, you're going to typically get a recursive loop in this situation. And this is because the way that they're calculated on the same time step. The overflow is calculated at time immediately at midnight on each day, as is the flow rate back. And so you can't, if you can see what I mean, this is recursion. You can't calculate one without the other. And so a way to work around this is to delay it. And this would be a case where I would say you want to use a, you want to use a material delay element unless you're not allowing unscheduled events, which we are in this case. All right. And even though we are allowing the unscheduled events, I still have a previous value element. However, this is being done for yet another reason that I want to bring up, and that is that sometimes it's useful to allow a recursive loop like this and not have a delay. Sometimes sometimes your time step is big enough and your volumes are small enough that it's important to not have a delay. Every once in a while this happens, typically in a more detailed process type model is where it's more important. For example, I was working on I was helping someone with a model that is simulating the recycle of water through a oil sands processing facility in which steam is pumped into the ground and then water is separated from the oil and cleaned, processed, and then converted back to steam and back into the ground. Anyway, within a 24-hour period, this has already recycled many times. The flow is, moving faster than around in a cycle, faster than within a 24-hour period. So because of that, what I mean is the storage elements were very small in comparison to the flows. So we did not have any storage elements. And so therefore a delay in the flow cycle would not make sense. We would need it to be instantaneous, and it requires iteration to solve for that kind of thing. But a basic way to do it in GoldSim is to simply refer to the previous value and then loop the entire flow system. And when I say loop, I'm talking about a looping container. So this whole system that we're looking at right now is in a looping container. And you can see up here in the address, it says looping container. The reason we do this is because we want the previous value element to be looking at the value from the previous loop, not the previous time step. And that's exactly what a previous value will do. Is it will take the last updated value, any update that has occurred, and on a looping container, that is the last update that occurs. So at time 0, for example, it will loop 3 times, and on the first loop, it will take the initial value, but then on the next loop, if the value is updated, then the reference to the recycled flow will be different. But then if you update another loop, if you iterate again, then it will update to its value. So depending on how many of these loops you have, it shouldn't take very many iterations before you're now referencing almost exactly the same value that is coming in on the loop. And so it's, I would say for many simple cases, this will work. This will work for you using a looping container. But there are times when it's more complicated. You might have loops within loops, and you might start to get into a situation where you need a solver, like a flow. You might need a flow solver to solve for a more complex coupled system. And so just be aware of that. It can be done, and I could show you an example if you wanted to see it, but essentially there are various ways. You could hack one in pretty quickly by, instead of a looping container just looping 3 times, it could loop until a convergence criteria is satisfied. An example of that might be, you know, assume that everybody gets the water they want, and then if you have a negative flow downstream where you're taking the water from, then you loop and you start cutting back uh, the supplies incrementally, maybe based on water demands or priorities of some sort. And then you eventually get to a point, you've iterated and cut enough people back that eventually you get to the point where you don't have negative flow, and that would be the convergence. It's a not very efficient way to solve it, because you typically just start at one end and just loop until you get to the answer. So we also have an example in which case you can use a solver, a root zero solver, for example, the secant method or bisection method or something, to get to the answer faster. So that is something you can do, but still not exactly what you might see in a flow optimization routine. In which case that would require setting up a matrix and doing something like a simplex method or something to solve for optimum flows, and that's a whole nother um, situation where we probably don't want to go. But just know that you could get into a very complex flow network, and if you start going that way, um, well, you'll have to consider building in a flow optimization there. So anyway, I would say it's more rare, but you should consider, if you're using previous value elements and you want to refer to the current value instead of the previous value, and you're only using a previous value element to get rid of a recursive loop, you don't want a delay, then you should consider using a looping container. See if you can get that to work, because it usually does in simple cases like this. And usually a mine water balance model, for example, is usually it's as far as flow loops go, it should be simple enough. It's not a real complex network typically. So okay, the next topic is rapid oscillations found at controlled outflows. Okay, so this is another topic that comes up quite often. So let me show an example model. Okay, here's a model in which we're simulating a pond again, and what we have is an upper bound called target, in this case 300. And what we want is, as water is filling this pond, we want to withdraw water only at the time that this pond is sitting at the upper bound. So you might think, well, that's pretty simple logic. It's just an if statement, and we say if the pond is full is an output of pond, right? It's a pool element. Pool and reservoir elements have this output called is full. You could also say if pond is greater than or equal to the target, right? The 300. So however you want to do it, it's the same. But this is full. We say if the pond is full, then we can start pumping water out. But if it's not full, then don't pump any water. So you can already see here, this could be oscillating, right? Because as soon as the pond hits full, it will then become not full in the next time step. But then because it's not full in the next time step, the pumping stops. So then it might go back up, and you might imagine it's going up and down on successive time steps at some periods of time. So if I run the model and look at the chart, you can see that if I expand this, you can see there's a lot of ups and downs going on here. Also, if let me just make sure I'm showing unscheduled events. Okay, I am. If you don't show unscheduled events and you run this model, then you'll see a lot less of pumping. But this is not the case. This is not what's happening. You can see that the reservoir is hitting the upper bound multiple times, but because GoldSim by default shows only the value at the basic step, which is midnight of each day, we don't show what's going on in between this, in between the lines, essentially. So now if I go back to edit mode and I change this model to show high resolution results and run the model, now what we should see is that it is including these unscheduled events, and it does. You can see that on day 65.4, we hit the upper bound. Therefore, we immediately start to overflow. Sorry, not overflow. Draw water out. So we have that pumping rate that starts only at that period. And then on the next day, we're just below, so it turns off. And then it turns on in 0.06 days, which is a pretty short amount of time. It turns immediately back on again. But these values, when it turns on, they're not going to be seen unless you enable high resolution results. So just keep that in mind. Anyway, the point is that with coupled storage elements in this model, that where you have water flowing from one to the other and they're talking to each other, and this is all very common in a mine water balance model. When this is happening, you could have an increase by an order of magnitude potentially of more unscheduled events, because one unscheduled event might trigger another one at another pond, and so on. And so you might end up with very many oscillations going on here in the model. If you enable high resolution results, you might see it might also just look like a solid blue all the way across because it's happening so often. That happens. And then you might start wondering, why is my model taking so long to run? And this would be why. This would be why, because you're inserting so many unscheduled events. So how do we get around this? Well, it turns out that on our website, we have the answer. We actually have multiple, because this comes up so often, we have multiple ways to learn about this issue and to deal with it. So the first place I'd like to show you is in our online training course. So if you go to Customer Care, Learning Resources, Training, then come down here to Free Self-Paced Online Training Course, and then scroll down, you'll see there's a whole bunch of lessons, well, units, and within each unit are lessons. It's a really good way to get a good basic understanding of GoldSim. But if you go down here to section 13, there's a lesson called using the status element. This is a great way to get around that issue of inserting time steps. And this is a very similar model to what I was just showing you. In fact, it pretty much is the model I was just showing you. You'll see that it's again, there are a few differences, but you can see it's inserting a lot of steps. Well, it turns out that a better way to do it is to simulate it with a status element, similar to how a furnace or air conditioning is operated with the motor turning on and off, being controlled by a thermostat, where it would also be using a deadband. And that's what we want, is a deadband. And a status element allows you to do it. It allows you to hold a status until you reach the upper part of it or the other side of this deadband. And kind of gives it a delay so that it's not oscillating so fast. And so that's a nice thing about a status element. And it also allows you to not insert time steps unnecessarily. So you can get both of those accomplished with the status element. And so what you would have is a target, and then this is called a dead band or band. And so what happens is it monitors this volume, and it waits until you get to the other side of the band before it switches. It's switching from on and off. And therefore, running that model, you get a result that is a lot more realistic, where your upper bound might be, you might be fluctuating around the upper bound, but not holding constant to it, and also importantly, not inserting time steps. Okay. All right. Oh, the other place I wanted to show you, I forgot, is I wanted to show you in the model library, we have another model that will also show that same thing. Those exercises that I just showed you, they can be downloaded. But if you go here to model of water management, you should be able to find it, or you can type in the search here, reservoir status, maybe. I bet if you just type status, you'd find it. But this is it, reservoir discharge controlled by a status element. So here's a model you can download that uses this very simple logic, very similar to that lesson. So you can get it in either place. This one is just a little bit more, it's got a time series inflow that represents an actual river that exists. So it's a little more realistic, but it's the same exact logic. It's using a status element. So that is a really good way to get around that, that issue. And what I mean is avoiding oscillations, avoiding rapid oscillations. Using a status element will fix that. Okay, the next concept I want to talk to you about is model file size. Oftentimes people are surprised by how big their model is getting, not realizing that there are certain little nuances or rules of thumb you should follow in order to keep your file size at a minimum. And that's really mostly driven by, obviously when you have gobs of data, that'll do it, but sometimes that can't be avoided. The other thing is images, things that are embedded into your graphics pane. And so I know I've talked about images before, but I just want to show a couple of examples just to drive it home so you understand completely what I'm talking about. So let's say we have a model file here, and we have this image that we want to insert. This is just a vector graphic here, and if you're wondering, there's two different types of images electronically. There's a vector drawing, and then there's a raster image. And the raster image is on the right. And the raster image, it can be of various file types: JPEG, PNG, right, BMP, etc. On the left is a vector drawing, which can also be different file types like SVG, Adobe Illustrator. In this case, EMF. EMF is the only acceptable vector type of drawing that's accepted in GoldSim in the graphics pane. So if your graphic designer is creating an SVG for you or an Adobe Illustrator, you're going to have to ask them to please, convert it to EMF, because that's just what GoldSim accepts. Okay, so that's the difference. And vector drawing is about math. There are equations used to draw the things, and pixelated is raster images are pixelated, and so that's the difference. And the raster image will take a lot more memory to save it. Somebody asked, do you have any tips for managing file size computation time when looking at very rare events, 1 in 10,000 it looks like, which require lots of Monte Carlo? Oh, okay, so that's a little bit different question, and I will get to that. Good question. So let me come back to it in a second. That's a little bit different situation than this one. But anyway, let me just explain a couple of things about these two images. So I have them both saved in this directory. So let me bring over File Explorer. And so the two files are located here. One's called Industry Raster Image. That's the raster one, JPEG. The other one is Industry Vector Drawing. Same exact thing, but you look at the file size different. One is 2 times the size. And you might say, well, gosh, that's such a simple image. Why is it so big? Yeah, we could reduce it, but sometimes that's just not even noticed. And it's hard to know, like, exactly how much can you reduce that size and still make it look good. It's all questionable, especially if you start to zoom. So for example, if I go down here and I start zooming in, then you can see that the raster, let me change this. Okay, you can see that pretty soon on the vector drawing, and maybe it's harder for you to see on your end, but for me, this looks crystal clear, the vector drawing. Everything is perfectly smooth, um, just great. It looks just as good. And if I go in even more, you can see the case is still the case. Whereas over here um, uh, on the raster image, it's starting to look like a early 1990s clip art, very pixelated here, right? So it's a difference. There's a big difference. And so when you have drawings that you're inserting, you should always try to make sure that they're vector drawings. And also take note that vector drawings can be very compact in size. This one is a tenth of the size of this pixelated version. So you can imagine that if you started, let's say you had a logo that was for some reason a kind of a large file. This has happened to me before. I didn't even realize it. And I was copying and pasting this logo into all these different containers. And then pretty soon I look at the model file size, and you can see here, here's the same file with the vector drawing copied many times. Here's the model with the raster drawing copied many times, and you see that it just grows huge, right? Because every single copy of that image is being added to the file size, multiplying it. So however many times you paste that, you'll get a multiplier of the big file size. So that's often the case with models. When you're not really thinking about it, you're adding all these cool graphics, and then all of a sudden you realize, whoa, it's huge. That's often why. So just try to always remember EMF. EMF is the style that you want, and also remember that it needs to come out of, that you should load the EMF in PowerPoint and save it as, there's actually two kinds of EMFs. There's the old EMF, and then there's the new EMF. And so in PowerPoint, if you bring in a vector drawing from somewhere, it's a good idea. I'm just going to do that right now. Copy, go into PowerPoint and paste. It's important to note that, hang on a second, let me just delete these other things so they're not in the way. Okay, it's important to note that you need to make sure this is converted to the latest EMF. So you right click, go to Ungroup, and it will ask you right here, do you want to convert this to a Microsoft Office drawing object? And that will update it to the latest libraries that you need. That will render very nicely in GoldSim. And so then you just right click and go to Save as Picture, and then save it as an EMF. So just follow those steps, and then when you load it into GoldSim, it'll be perfect no matter how you zoom, and it will still be a very small, relatively small file size. So that's a good way to save on that. Okay, so let me address the question of Monte Carlo. So let's say you have a model, a very complex one that needs to simulate 10,000 or 100,000 or 1,000,000 realizations, and it's taking a long time. Well, the first thing you should do is run just a single realization and do everything you can to minimize the amount of runtime for that one realization. So do that first. Try to find things. If it looks like it's bogging down, a good culprit is rapid oscillations. So check for that, like I just mentioned, doing those things. Look for, you have to enable your unscheduled events and look for places that are inserting a lot of events, and do you want them? And if you don't, then add some logic to the model that prevents them from occurring. But if you have to have them, you have to have them, and that's just your runtime for one realization. But if you've exhausted all those avenues for a single realization, the next step is then to use distributed processing, I think. That's really the answer for Monte Carlo simulation. You want to use distributed processing. And GoldSim by default, just your basic GoldSim commercial license, it comes with, it's called DP Lite, distributed processing Lite, and it allows up to, I think it's 10. It's either 4 or 10. I think it's 10, up to 10 client, well, we used to call them slave processes. And but in the next version, you'll see the terminology has changed. But anyway, those will then run the realizations, unique realizations. So they'll each take a batch to run at the same time, and then they'll roll them back up into your main GoldSim and show you the results for all the realizations. Essentially, just doing uh, parallel processing. Essentially, is what it's doing. So you're distributing multiple realizations over different computers. And so you can do that with computers connected on your network, but you could also do it on one computer where you have multiple cores. So in my case, I can have up to 4 processes running at the same time on my laptop. So in that case, I could run 3 slaves and have one master GoldSim and distribute my realizations to those 3 processors, and then they would roll the answers back up. So it would reduce the runtime by 3, a factor of 3. So that's pretty useful. And they would all just be using my one computer. But if you have a network of computers or servers or something out there in your company, you could install the player on those computers, and you don't have to buy any extra licenses for it. But then you could you could have realizations being run on those computers, and then the results are then brought back over the network to your master controller, GoldSim. So that would save a lot of time. Okay, the last thing I want to talk about here is licensing issues. So, and this is a topic we tend to avoid in webinars because it's oftentimes not something that that you as the end user needs to deal with too much, but sometimes you do. So it just depends. But one of the issues is, and I'm going to refer back to an article or a place in our help center. If you go to our help center at the very top level, there's a thing here called license help. So if you go here, I would recommend looking at some of these issues. But you'll see also there's a troubleshooting section. If you go in there, it gives some very common errors that we see from users. One of those is, for example, unable to connect to the server, stuff like that. It's very common. But also, under basic licensing tasks, there are things that are probably useful. They're very basic, but like how do I activate? Because these are not things you do very often, right? And how do I connect to a network license? That's a common one. So if you click on this, it will show you all the steps that you need to do to make that connection. And so, for example, in my GoldSim, I go to Help Licensing, and here for me, it shows that I am currently connected to a standalone license. The reason I know that, even though I have an address for a network license, I know it because up here under Acquired License Features, it shows me the license that I have, and it does not say anything about a network. So I know I'm grabbing a standalone license, and that's the way that GoldSim works. Is it first looks for any available standalone licenses, and if it finds it, it'll plug that information in here, and it will show the license up here. However, if that local license is not found for the particular version that you're running, then it will revert to looking for a network license if you have one. So that's the order in which it goes. So I'm just going to copy this activation and return the license. The reason I want to return this license is because I want to show how it's connecting to the network license. And so what it did is it just returned the license, and you can see there it says license successfully returned. And now as soon as that happens, well, it says I don't have a local license. Now I'm going to go down to the next step, and I'm going to look for a network license, and it finds my address here, and sure enough, at the top, it shows network in parentheses. So now I know I'm connected to the network. Just keep in mind when you're trying to connect to a network license, those of you who use one, keep in mind that the address must have this syntax: port number at the computer name. In this case, it might be your server name, but you have to have this correct port number, and that is maintained by your license administrator. You'd have to get that from them. But this is often forgotten. People are often asking us what this is. That is the syntax that you have to use, and you have to get that port number from your license administrator. That is not something that we know. It's distributed by them, maintained by them. Okay, so also often what happens is people get this error message. I go back up here to troubleshooting. Oftentimes, let me just look for this is probably the most common license question we get from people. And it's this one right here, reason 7174. So this is probably the most common thing that happens is, no, it's not. I'm sorry, not deployed only. This one, 7288, fulfill count. I mean, that one does happen, but this one is the most common. Well, okay, they're both, sorry. Let's first talk about this one where the count is exceeded. Okay, so 7288, fulfill count exceeded the available seat count. What this means is that you are trying to, I would say, most of the time, I would say 95% of the time, what this means is when you get the 7288 code, it means that this license is already activated on a different computer right now. It's already been fulfilled on a different computer. And the reason it's so common is because, you know, people are leaving the company, people come and go, or a laptop is reformatted, you get a new laptop. All of these things can happen and you forget, but the license was never returned on the old computer. This is just so common. And so then you go to try to, you know, activate, and you get this. And it's because you didn't return the license on the old computer. So it's always just important, like if you're kind of planning ahead, you know, thinking about, okay, I'm going to get a new laptop, it's always just set a reminder, you know, return all your GoldSim licenses off this computer before you say sayonara to that laptop. Just FYI. So that's common. The other one is only deployed items. So sometimes your license will expire, and we will then renew your license. We do this annually for every single license, and we issue out a new activation. Well, if you didn't get that memo, you didn't get the new activation, and you still have the old one, and you're like, well, now it's time to activate, and you try to do it using an old one, you'll get this message. It'll say it's not deployed, meaning we deployed a new one, and this is now you're using an old one, essentially is what this means. But anyway, if you ever run into these issues, you know, you can always ask us, or you can just type this number 7174, you know, whatever the reason is in your error, you put that in our search, and you should come up with, you know, an article. You should most likely come up with an article that talks about it, and it says in here what to do, what the solution is. So I highly recommend just looking for that. Okay, somebody asked, what if my laptop dies? Yes, also very common. So it gets stolen or it dies. In that case, you're just going to have to come to us. There's no other way around it, because you're not going to have a new activation, right? It's dead. And so the only solution there is to come to us. And so you can just go to our website, go to customer care, and go to just technical support. There should be a button down here somewhere, right here, submit a request. Just click on that, and then just tell us, here's my activation ID. My computer died. We might ask you for a form to fill. It's a very simple form. You fill it out, and then we reset the license. Sometimes we ask for that, but Anyway, it's pretty simple, and we realize it happens, so it's no big deal. Somebody asked, is there an online guide to DP Lite? There is a guide, actually. So what I would recommend that you do is go to, let's see, Learning Resources, Customer Care Learning Resources, and then Documentation, and then Manuals. So go to Distributed and Processing, and this does cover. You'll use the same concepts in this user guide. So just follow that user guide. Just keep in mind that your number of processors running are going to be limited to 10. So that's the only difference. Everything else, all the other concepts will be the same that you'll use here. So that's where you go for that information. I hope that helps. Okay. Any other questions? All right, any other questions at this time? All right, well, if that is the end of the questions, then I'll go ahead and end the webinar. I will be posting a recording. Oh, what? No, another question. If you're in your first example in the spreadsheet, how did you output? Okay, let's go look at this spreadsheet. Okay, so this thing, let me close the, okay. So the question is column E. Oh, okay. Yeah. So it just turns out that we have an element in the GoldSim model called timed event, and it has an output called event count. So the cell I have highlighted right now, that's the name of the output. And I'm just, yeah, you want to see it? Yeah, okay. So let me open up that model. This model is cumulative results. Okay. Okay, so in this example, the one thing you want to keep in mind is that it's just I just contrived it to just do a very simple thing, but it's supposed to represent a big model that's doing a lot of things. But the point is that it has unscheduled events that are occurring, and so let's see. Still waiting for this. Why am my laptop is sounding like it's working really hard. Oh, because I just killed the license. Okay, sorry about that. I just killed my license because I turned my VPN off. So let me turn that back on. Okay, so it thinks I don't have a license. So yeah, something that I mean, this is a realistic thing, right? This happens from time to time. Okay, I started shutting things down, and then I did that too early. All right, okay, my VPN is back on. Okay, so here's the model, right? We have a flow rate inside this model, and then we are calculating the cumulative amounts. Okay, so the question was, how did we get column E in the spreadsheet? And that was simply just telling us the number of times that we have an event occurring. This is not necessarily an output that you'll have in a real model. Although you could, if you wanted to, for example, tell me how many times we hit the upper bound, right, on a reservoir. And then you could add all of those up and you could figure out how many inserted events you have. You could calculate that. But in this very simple model, all we're doing is if I go in here into this container, all we're doing is we have a timed event. and it's just inserting random events every 10 days, right? That's all it's doing. And so on this output port of this event, you'll see there's an event count output, and you can see that over the course of, well, we'd have to actually run the model to see how many times. Let's see how many times it actually. So it outputted 7 times during this simulation. This is 7 unscheduled events occurred in this particular model run. And so in a real model that's hitting the upper bound, I would say the way you would gather that information, we should just go to that pond network model. So this model, yeah, that license is still having. Okay, so in this pond flow network model, if we wanted to find out how many times we're hitting this upper bound, then we could add, for example, we could add an event, a triggered event here, and we could trigger this to be, we could say on changed e time. No, let me think about this for a second. I think if we just said at stock test, and then I need to remember what the maximum or what the upper bound is. It's called pond capacity. Okay. So if I said at stock test, this will insert an event exactly at the point in time in which this thing occurs, which is pond 1 is equal to or greater than or equal to, and then we say we have this thing called pond 1 capacity. So at exactly that point in time, it will trigger an event. So when I run this model, now what I should be able to do is I should be able to click on the output port and look at the event count and find that, okay, it hit the upper bound 14 times. So that would be a way that you could find out how many events were triggered by this one element. Now there might be events occurring on other elements, but that's how and then you could add these all up, by the way, by using a discrete change that is triggered by this event. In fact, you could just trigger you could just replace this triggered event with a discrete change that is triggered exactly the same way, and then just put all those into an integrator, and it would count the total number of inserted or total number of times you've hit the upper bound on all your reservoirs, for example. That's something you could do. So anyway, I hope that was useful. I didn't want to go too far into the weeds on that, but hopefully that was useful for you. All right, great. Good question, though. I think that's probably it. Looks like people are starting to leave. So yeah, you can always follow up with questions later. Thank you for joining, and I hope you guys can join me next month for the May webinar. Oh, in fact, we should look at the schedule because I think we have a guest speaker. Let me just see. In May. We do. So Ted Erie is going to be talking about a model, a GoldSim model that connects FreakC with GoldSim using a Python interface. So he was saying that this might be a bit simpler than the existing example that's in our library. I don't know anything about FreakC really, but Ted would be able to answer any questions about it and how the existing model differs from this one that uses Python instead. The other one uses, I guess, C, I think. So this, if you're doing geochemistry in your models, this would be probably a really good webinar, but also if you are interested in incorporating Python with external tools or just linking a Python program script that you can then couple with GoldSim, you might want to attend next month's webinar. So we will make an official announcement about it later. If you're on our email subscription list, you'll hear about it. We'll also make announcements ahead of time, but just stay tuned. All right, thanks for joining, and we'll see you next month.